So in this video I'm going to explain the difference between the actual vapor compression cycle and the Carnot cycle. As I have explained before that in a Carnot compression cycle we are in wet compression region, and during compression we have a mixture in between liquid and vapor phase. So in actual vapor compression cycle we are in saturated vapor state when we are going to compress the refrigerant, whether it is ammonia or it could be any refrigerant or 120 112 or anything. And the other is the second point, isothermal heat rejection is replaced by isobaric heat rejection. That is mean that we have here in this that in actual vapor compression cycle there is only single compressor that is used to increase the pressure from lower pressure to any higher pressure and in superheated region. So by desuperheating we means to say that we have an isobaric heat rejection. So there is no intermediate pressure by which we don't need of any second compressor, which was in Carnot compression cycle, that is isothermal heat rejection, but that is actually replaced in real compression cycle, that is isobaric heat rejection. Now the other point is isentropic expansion in turbine is replaced by isenthalpic, that is throttling expansion, because as I have explained in the TS diagram, that if you remember or if you can have on your notebook the TS diagram of Carnot compression cycle, then from through state 3 to 4 we have in Carnot cycle an isentropic expansion, but in actual we have isenthalpic, that is there is an increase in entropy and decrease as long as in decrease in pressure and temperature. We have isenthalpic, that is the increase of isentropy, decrease in temperature and pressure by maintaining a constant enthalpy from expansion valve, or you can say a turbine, through a drop of pressure maintaining the constant enthalpy. So these are the differences in these three bullets I explained. So moving down to the next slide. So here you can see from state 1 to 2 we are in superheated region, and there is no intermediate pressure, no need of another compressor, and there is an isobaric, only a single pressure and a condenser through this pressure, and there is a isobaric drop or a heat rejection, and this line at state 3 to 4 is an isenthalpic drop and increase in entropy, drop in pressure and temperature of the refrigerant, and this is the same as the evaporator heat taken up. So now the comparison, that what would be the effect or losses or the advantages or disadvantages. So the first of all is the refrigerating effect, that what would happen to the refrigerant or the you can say the coefficient of performance of actual cycle and Carnot cycle. So you can remember here that 1, 2 double dash, 2 dash, 3 and 4 dash, and from 4 dash to 1 is Carnot cycle, and from 1 to 2 and 2 to 2 dash is the natural actual compression cycle, and 3 to 4 that I already explained. So you can see here that we have an increase on work on a compressor related to the relative comparison with the Carnot cycle, and here this is actually the refrigerant effect, that from state 1 to 4 and 4 dash, here from 1 to 4 we are in actual, at this you can say rectangle, we have taken heat from the environment, and from 1 to 4 dash you can see a lot, that is a difference, a bit difference, that is 4 dash to 4 is taken by the Carnot cycle. So we can say in actual the refrigerating effect is decreased, and in Carnot cycle we have a little bit increase in the refrigerating effect. Refrigerating effect is actually the heat taken from the environment and cooling down if we are refrigerating else, or heating may also, but we are only specific in this that we are cooling the environment. So actually the refrigerating effect here is cooling the environment, which means by taking heat from the environment, that is to change the state from mixture to the saturated vapor at state 1. Another that is effect, see the refrigeration effect decreases, I already explained. So going to the another point, that is the heat rejection. Heat rejection, what we means that here we need to have a increased in compression work. From 1 to 2 we have a high work must be, we have to done a lot of work, and from 1 to 2 double dash we have less work done, or the compressor. And you can see from 3 to 4 dash there is a turbine which is used to which is useful to take work from the turbine and to use in a compressor. But here there is less work is taken from 3 to 4 as compared to 3-4 dash, that was the ideal Carnot cycle. But 3 to 4 there is a less work done taken given from this, and here a lot of work is done to increase the pressure in actual compression cycle. So here you can see that Q rejection is more. Q rejection is more because here area 1 is adding to it. So manually we actually what we are saying that the rejection of heat in Carnot cycle is less compared to the actual cycle. So actually we are rejecting heat a lot, but refrigerating effect is less than rejection. So actually we means to say that our refrigerating effect is not that much as it is in rejection. So actually heat rejection is the temperature environment effect, that is the increase of heat in environment. Another point is the compressor work input, that in actual we have, I have explained in the second bullet but earlier, but what can I say, that in this we have in actual compressor we have increased work because on this pressure line, and on Carnot cycle we have this two compressors, there is an intermediate pressure line for 1 to 2 dash, and then we have isothermal compression from 2 double dash to 2 dash, which is a ideal case. And here this work taken up is less, and input as an input is less, and to the compressor is obviously we need to have a higher work done compared with the Carnot compression cycle. So we have now superheat loss and throttling loss. Superheat loss, what we mean that increase only work input does not affect refrigerating effect. So actually what we are saying in these are the different types of refrigerator dome, but I will explain only the first type, that the superheat loss is, we can say desuperheating, that this 2 to 2 dash or 2 double dash to 2 dash is increase only work input. So in actual you can say that from 2 to 2 dash this is a heat loss from superheated region, that's why it is called superheat loss. It means that from we are moving from superheat to saturated vapor state, and there is a loss of heat, or we can say a more work has to be done on it. And another one is the throttling loss, which increases the work input and decreases refrigerating effect. It means that here at type 1 you can see 3 to 4 dash is the decreasing refrigerating effect, because actually it had to increase from 3 to 4 dash So from 4 to 4 dash there is a decrease, from because 1 to 4 is a less distance and 1 to 4 dash is a longer distance. So 1 to 4 dash, which is a longer distance, we means that the effect of refrigerant is greater as compared to the 1 to 4. So this is actually the effect of throttling and superheat loss on different dome types, but I will not explain the types of refrigerant. In next lectures inshallah I will explain, but our main focus is on how to compare the actual and Carnot compression cycle. So here is the coefficient of performance COP, actual cycle, and COP of Carnot cycle comparison. That so mainly coefficient of performance of Carnot cycle is obviously greater than actual cycle. So and the question arises that why we are not explaining the efficiency and saying only the coefficient of performance. So the main difference between efficiency and coefficient of performance is that in efficiency we are calculating the work input, or we can say the heat added. For example, in Rankine cycle, the heat added to the system and the work done output from the steam turbine. So we are actually calculating the energy, or you can say the work outputs. But in this coefficient of performance in a refrigeration cycle, we are only changing the state, or we can say we are taking the heat from an environment and transferring it to the another place, or we are cooling our environment and increasing the heat to the other environment, as in air conditioning of our rooms and in halls, etc., or different places in hospitals. So we are only interested in the transfer of heat from the environment from place to place, or you can say environment is too much. So from place to place we are transferring the energy. So we are not studying the amount, or what can I say, that how much energy is leaving or entering the system, but only the transfer and the work required for the compressor and the expansion valve output. So actually we are not interested in the efficiency, that how is the efficient, but only the performance of the compressor, condenser and expansion valve, that how much they are performing their duties to transfer the heat from one place to another. So that is the difference between coefficient of performance and efficiency. Now this is the analysis of vapor compression cycle. Simply evaporator, compressor and condensers. The work input are the heat rejection and heat taken from the environment. These are simply the enthalpies and the mass flow rate of the mass flow rate of the refrigerant, and Q evaporator is the heat taken from the environment, and condenser is the heat lost to the environment, and the compressor work that is done. And the coefficient of performance is simply the formula given. I will not explain because the formula is just the value put. Now the effect of subcooling on refrigerating effect, as in these are the pH diagram and TS diagram, that how we can increase the effect of refrigerant. That if we go and you can see pH diagram from 2 to 3 and 3 to 3 dash, we are in subcooled region, and from 3 dash to 4 dash we have down an isentropic process, we can say. Or if not, then you can see in TS diagram that from 3 to 4 we are in actual compression cycle, and from 3 dash to 4 by subcooling we means that we are lowering the temperature of the liquid after condensing it. So after condensing and subcooling it through this state from 3 to 3 dash and lowering its pressure and temperature to lowering its temperature and pressure, you can see 3 to 3 dash there is a pressure difference and a temperature too. So from 3 dash to 4 we have increased its cooling effect from 1 to 4 dash, which is greater than 1 to 4, you can see obviously in TS diagram. So effect of superheating. So effect of superheating increases, you can see here when we are not superheating region, we have here from saturated 1 to 2, and we have this refrigerant effect from 4 to 1. If we increase the temperature from 1 to, let's suppose say 1 dash here, or we can say here evaporating it. So in this compression from 1 dash to 2 dash here, and from here 2 dash, you can see from 4 to 1 dash we have increased this net work, which is the increase of refrigerating effect. That is, it can take heat from the environment and it changes state from saturated vapor to superheated vapor state. So that is also the effect of superheating, to increase the refrigerating effect, or taking another by means which easily I can say, in other words, that we can take much more heat from the environment, or cooling it from state 4 to 1 dash. Herein we move to superheated region. So that is the end. Thank you very much.